Okay, so quick announcements about the first exam. All right, I originally said, I think it was probably the first day, I said, we're probably going to have one around the 8th class on September 10th. What I'm going to do is I'm going to push that one day ahead. So we're going to have it on Tuesday, September 15th. All right, so if you want to jot that down, it's going to be Tuesday, September 15th. Everything's sort of fluid with exam dates just because you don't know how long something's going to take to cover. So the plan up until that first exam, and I'll give you the entire period to do it. So you come in, I'll probably take roll real quick just to make sure everyone's here, and then poof, we'll get that exam out. And so my plan is today to finish section P5. It's only one more topic left, and start P6 and then give you that quiz. Tuesday we'll be finishing P6. And then all I want to do next Thursday is, if I don't cover something from P6, I don't get to it, I'll cover that at the beginning of next Thursday. But then I'll use that day as a review. All right, I won't always do review days, but I feel like just timing-wise it works out to have one. So please come that day with questions, and I could solve problems with you, whatever ones you think you're having trouble with. Next Thursday is going to be the day to go over that. And then, like I said, Tuesday, September 15th will be our exam. Okay? Cool. All right, so we're going to finish off this section P5 on rational expressions. And I'm just going to sort of review what we've done already and then make one comment about the homework. Well, it wasn't really homework. It was just here. If you want to try these reduction of rational expression problems, why don't you try these ones at the end of the section? So all a rational expression is a ratio or a fraction or a quotient. All those things mean the same thing. It's a ratio or a fraction containing polynomials. So what you do in these problems is just reduce the rational expression to lowest terms by factoring the numerator and the denominator. And then if you have like terms in the numerator and the denominator, you can cancel those out. And then you'd be left with something like 3 divided by x minus 2. And I was finding the domain of the reduced rational expression. Now, I didn't realize it, but the book was asking you, this was on page 58, 9 through 23, it was asking you to find the domain of the original rational expression. So just everyone pay attention to this. On the quiz today, when I have you do this, I only want you to find the domain of the reduced rational expression, not the original one. Does that make sense? Okay. Now, why am I making that distinction? I probably should show you that out. Well, do you see this line right here? This 3 times x minus 2 over x minus 2, x minus 2. In this case, you had 2 x minus 2's in the denominator. Actually, let me find a better example. Let's see. Yeah, this one right here, where you have this 3x plus 1 that we cancel out. Well, in the original rational expression, this 3x plus 1, if that binomial was 0, you would still have an undefined rational expression. So if you solved, what x value would you need here? You would need a negative 1/3, okay? But I'm only concerned with, once you do the reduction, to determine the domain of that reduced rational expression. Does that make sense? Is everyone okay with that? So you do that process I showed you the other day, and then find the domain. All right? So this is what is going to be part of the quiz today. Just, you'll be given a rational expression or two, make the reductions, find the domain. All right? Again, these quiz questions are meant to just check to make sure that everyone's sort of on the same page with at least knowing what the process is. All right, then and then I talked about the quiz, and here are basically the different types of things you could see on it. All right, and we went over that extensively. Now, the next part was multiplying and dividing rational expressions, but it turned out that dividing rational expressions, we transformed that problem into just a multiplication, right? Because what do you do in this situation here where you have like a fraction divided by another fraction? you flip the numerator and the denominator, right? So you see how that, well, there's already a mistake. Right here, that should have been a C, right? Oh my goodness. Technology is great, but then sometimes, that happens. So that's supposed to be a C. And then because you flip that second fraction, you can just change this to a multiplication. All right, so all those problems are pretty straightforward. Again, you do all the factoring, that's your first step, and then just multiply across numerators. And since they're already factored, you're kind of just clumping them together, because you'll see that I just kind of draw that line over where that multiplication symbol was. And then again, reduce the final answer so that you have some things cancel out, and then there it is. All right, so that stuff's not going to be on the quiz, but that was the last thing that we did in section P5. So the last part of section P5 is going to be, so this is new, adding and subtracting rational expressions. All right, so there's two different versions of these that we're going to work with, and we'll do the easier one first. And we'll just look at regular rational numbers first, so just fractions. So if you had something like this, we can kind of call this like rule number 1, I guess. All right, rule number 1. If you had a fraction that looked like a over d plus c over d, how are you allowed to combine those two fractions? If the two fractions have the same denominator. Yes. Yep. As long as your denominator is the same, right? The numerator of the addition here would just be a plus c. All right. Now that rule will work with polynomials as well. Now what you could also say is if you have that same situation, so a over d minus c over d, the only thing that's different is that you have a minus c. Now where I see a lot of issues is when you subtract c, if c is a polynomial, and let's say it has 3 terms, that negative sign is going to change each sign on each of those terms, right? And I'll show you an example of how that works. But these are pretty simple, so let's just dive right into one. So we'll call this example 1 for this rule. So you have 2x plus 7. They're weed whacking and cutting grass outside, so if you hear strange sounds coming from over there, that's what you're hearing. Okay. All right, so here's an example where you're subtracting polynomials. Well, rational expressions that contain polynomials. Now, first thing to do is to check to see if the bases are different. So by base, I mean denominators, right? So they're the same denominator. So the 3x plus 2 remains on the bottom because they're the same. And now you have to just do that subtraction up in the numerator. So you have 2x plus 7 minus. Now I suggest you do this every time, even if in your head you know what's going on. Put the minus sign there, and then in parentheses, put that next polynomial, which would be x minus 2. Because hopefully that will remind you that, you know what, I have to distribute that negative sign through both terms in x minus 2. So then you have 3x plus 2, and then what do we get up here? 2x plus 7 minus x plus 2. And then we're just simply left with, on the numerator, 2x minus x is going to be x, and then 7 plus 2 is 9. So x plus 9 over 3x plus 2. And then that would be our final answer. So this would be combining, right, rational expressions using addition and subtraction. Okay. Now these will be all pretty, and if we were doing addition, that'd be even easier. You would probably skip this step of having to worry about the parentheses, right? Because you would just be able to add immediately. Now, here's an example. Is everyone okay with that? It's pretty straightforward, I hope. Example 2. Now, this one's a little funky. Okay, so in this one, are the bases the same? They're not, right? But is there something you can do to make those bases the same? Could you do this in this first one? I don't know. In my head, I always like to see that x variable first. Like, so the denominator of that second term, x minus 1, I kind of like the way that one looks. So I want to try to see if I can get the denominator on that left rational expression to also be x minus 1. So could I do this? Could I factor out a negative 1, and then this will then become negative 1 plus x? Can I do that? Is that mathematically allowed? Oh yeah, right? Now, isn't negative 1 plus x the same as x minus 1? Right, they're the same because you can interchange things in addition and subtraction. So here's what I'm going to just go through each of these steps. Now, what happens to that negative 1? Well, it's now a part of that fraction. But do you see how the numerator is negative 2 and the denominator is negative 1? What's going to happen to those negative signs? Yeah, because if you had negative 2 over negative 1, what's your solution? Just a positive 2. So I'll rewrite this first rational expression as a positive 2, and then I'll just flip the order of what was in the binomial in the denominator. So now I have a situation where I'm back to the simple addition, where I have the same base. Now, what I could do, keep the base x minus 1, and now I just add the numerator. So it's 2 plus 2 minus x, which is 2 plus 2 is 4, and then it's minus x. Now, I've seen this on quizzes. This is not a distribution. The only way I would distribute 2 through that quantity 2 minus x is if I was multiplying, right? But I'm not multiplying. I'm simply just adding. All right, so they should be fairly simple. The only wrinkles they'll throw in is if you have to, in this case, these are opposite in terms of sign, so then pull out a negative 1, and then you'll end up getting what you need. All right, so they're the easy ones. Cool? Awesome. Okay, one more rule, and then a couple problems, and we'll be done with P5. All right, here's another rule. We'll call this Rule 2. Because again, when you're doing homework problems or seeing problems on quizzes or exams, I want you to be able to think, okay, well, if I'm adding rational expressions, which rule do I have to go back to and remember? Here's this rule. Now, if you had a over b plus c over d, okay, can I just add the numerators in this case? You can't, right? Can't do it. All right, so somebody asked me the other day, I don't even know what the question was about, but it was like, oh, can you cross multiply? I forget who that was. Maybe it was Tom. I'm not sure. It might have been Tommy. I don't know. Yeah, somebody answered a question, sorry. So here's what you do with these problems. The easiest way to do this is to simply go, all right, a times d plus c times b all over b times d. If you do that, you will always get the right answer once you go ahead and do all these operations. Okay. Now, that's not always the most efficient way to do it, but it works every time. I tend to like rules that apply universally. I don't like rules where it's like, oh, well, this rule only works for this one particular situation, because then you have to end up remembering a bunch of situations. You might as well learn how to do these problems using one rule, and then it just becomes simpler for you to remember what to do. All right, so, and then also I'll do this just so I don't have to write it out again. This also goes for if this was negative. If you've ever seen the plus or minus symbol before, it just means you can interchange that equation with the addition symbol or the subtraction symbol. All right, so let's give one a try. All right, and again, if we notice, yeah, let's just go ahead and do one. And we'll leave the rule right there, and you'll see how it applies. So here's example for rule 2. We have 3x over x minus 1 plus x over x squared minus 1. Okay. So here we go. Let's do the general rule, and then I'm going to show you another way, only because if you notice it, it could, be quicker on a quiz or exam. So let's try our rule. We're going to have, remember, we're going to do a times d. So here, I'll throw these letters here just so you know what we're looking at. So there's a, b, c, and d, right? So the first thing in our formula is a times d, so we're going to do 3x times x squared minus 1. And this is addition. C times b, x times x minus 1. And then it's going to be all over b times d, or x minus 1 times x squared minus 1. Okay. Now, to be honest, that doesn't look terrible. Okay. Now, the next step would be, can anything be factored? So there's a couple things here. I can't do anything with this 3x, but can I factor x squared minus 1? What does that look like to you from the factoring section? It's the difference between two squares, right? So you could take the square root of x squared and get x, and then the square root of 1 is 1. So this can become, right? And then we have plus x times x minus 1. Okay? So far, so good. And then I could do the same thing. Oh, right? Because I have that same x squared minus 1 term here, so that could also be factored to x plus 1, x minus 1. Okay? So far, so good? Okay. Now you have these terms in both the numerator and the denominator. Let's look at the numerator first, because we're not going to change much in the denominator right this second. Right, that's already fully factored. Can I factor anything else in the numerator? Because I have two terms. I have this 3x term with the x plus 1s and x minus 1s, and then a plus x minus 1. So is there a GCF between those two terms? I can't take a 3 out, but can I take this x that's sitting here out? Can I do that? Yeah, I could take an x out. And then what else? Do you see that both of these, so I'm just going to put a little box around them here. These are the two terms. Do you see that they both have an x minus 1? So I could factor out an x minus 1 as well. And then let's see what we're left with. I'm going to start using some square brackets here. We'll be left with a 3 times x plus 1. And then, what is this? And then we're left with, let's say, plus 1, right? That's all that. We basically took that entire second piece. Now that we're factored, can anything cancel? What can cancel? Yeah, see these x minus 1s hanging out here? They're gone. And then here's your final answer. Because when we do these, we typically want to leave them in factored form. So the denominator is already factored. And then what we have left in the numerator is that. Now here's a great question. Can I cancel out the x plus 1s? You can't, right? Because there's multiple terms up there, and each term doesn't have an x plus 1 term. Okay? So that would be our final answer. Now, sometimes the book might give you that numerator in a different form. Like it might actually just multiply all that stuff out. But this is how we want to see our final answers. We want to have a final answer that's factored. And that sucker's factored. All right? All right, let's do another one. And you'll notice, like, these take a little longer just because there's a lot of different things we have to do. So here's example 2. So what we're going to do is we're going to, let's see if I want to change this at all. I'm going to change this to a subtraction, just to give you an example of that. Okay, so let's go ahead and let's factor first in this case. Like in this other one, we could have factored, and maybe we should have done that, but it worked out in the end. Let's factor this one first. So I can't factor 5x plus 1. I can factor the denominator here, though, and take out a 7 and be left with 1 plus 3x. And then I'm going to do subtraction 1 minus x. I can't factor that. And then we have, I'm going to take a 3 out, and we're left with 1 plus 3x. Okay? So here we go. Now we're ready to go. We're going to do our, here's A, here's B, here's C, here's D. First thing we're going to do is A times B. So we'll have a quantity 5x plus 1. And we're going to have 3 there, so I'll throw the 3 out front times 1 plus 3x. Okay, we're going to be subtracting. So we're subtracting C times B. So 1 minus x times, and I'll put the 7 out front, times 1 plus 3x. And now all we said we were going to do with the denominators were do B times D. So we have 7 times 3, so that's going to give us a 21 times 1 plus 3x. And really, we could leave it like this if you'd like, because it'll be easier when it comes time to canceling some things out if you leave it like that instead of having it squared. But you could write it as 1 plus 3x squared. You could. All right. So far, so good. All right. Now, all we have to do, I'm going to leave the denominator the same. Can we factor anything out of the 2 terms that exist in the numerator? Are there any terms that exist in both of, so like terms in this thing and then terms in this thing? Is there anything? Yeah. We can factor out a 1 plus 3x, and here's what we'll be left with. 5 times, or it should be 3 times 5x plus 1. And then, let's see, it's going to be minus 7 times 1 minus x. Now, what could happen to that 1 plus 3x we just took out? Can't that cancel with one of those? Right? So what we're left with here on the denominator is just a 21, 1 plus 3x. And then we have a factored numerator. Now, if you're one of those people who don't like to see things that you could distribute here, you could go ahead and do that. So you could do, let's see, 15x plus 3 minus 7 plus 7x all over 21, 1 plus 3x. And then just simplify that numerator. You would get, it looks like 15 plus 7, so 22x minus 4 over 21 times 1 plus 3x. Okay. But I would accept this as a final answer, or that, you know, whatever your preference is, but I'd rather have the ones that are factored, because we're making sure you can do factoring and adding these rational expressions. So when we get into the content of chapter 1, chapter 2, chapter 3, some of these processes are going to come back. Now, luckily, the processes you're going to see in those other chapters aren't going to be as, you know, stringent and difficult as these ones, which is a good thing, I think. Okay, so let's see. That one's fine. We just did that one. Okay. Do you think you need to see another one of these? Does anyone want to see another one? All right, perfect. So here's what I'm going to assign as homework for section P5. So this is homework P5. Now I'd like to collect this on Tuesday. And this will be the third homework collection for exam 1, which means if you've all done the homework, and I have those grades up on the D2L site, you're going to get 6 bonus points on that exam, which is quite a lot, okay? It's quite a lot. So homework for P5, I have it right here. Now, this will be a shortish homework assignment only because I've already assigned 9 to 23 odd, right? I already done that. Like I suggested doing that the other day. And then what we'll have left is 25 to 39 odd, 45 to 51 odd, and then 69 to 77 odd. And again, don't worry about any other topics that I did not cover in this section, right? So that's going to put section P5. Are we okay? Yes. Sure. And actually, before anyone goes, if anyone wants to take a picture, it's going to be page 58 and 59. Okay? And if, again, please come up after you hand in your quiz today and take pictures if you need that. So what we'll do on Tuesday is I'll be ready to answer questions about those.
So 9 to 23 on, should that be submitted when we do the homework, or no?
Well, I gave it to you as a practice review for the quiz today. So yeah, I'd like you to hand it in. Yeah. So if you did it already, that's sort of a bonus that you've already had that completed. Okay? All right. Beautiful. All right. So that is P5. We only have one more P section, and that's what the first exam is going to be on. It's going to be on all these P sections that we've been covering. Okay? So we're going to move on to P6. So I already have it ready here in my notebook. And again, if I want to try to start handing the quiz out at about 9:20. So keep an eye on that clock for me, even though I am also doing that too. Okay. So, section P6, it is on rational. So again, we're just talking fractions. Rational exponents and radicals. Okay. All right, so there's some things we've already actually been doing. Like when we do the difference between two squares, in order to do that, you do know you have to know how to take the square roots of numbers. So let's just talk quickly about square roots. So if you have something like 4 squared, we know how to do that, right? That just means we're multiplying 4 into itself twice, and we get 16, okay? So the square root is reversing this process. So exponents and radicals are tied together mathematically. So again, in order to reverse the process, we're going to use the square root symbol, right? So we know what that looks like. And this is called the radical symbol. So if you wanted to reverse the process of 4 squared equals 16, you would do this. Square root of 16. And then we would say that was 4. Now, does anyone know an issue with what I just did? Is the only answer to what I just did 4? No. What would be the other solution? Yeah, so this 4 is really minus 4, right? You get 2 solutions when you take a radical. But now we call 4 the principal root. Right, so the positive ones are principal root. Right. So when we use numbers, it's pretty easy to tell if something's going to work with the radical. But once we start looking at variables, like let's say we had the square root of a, right? And we wanted to say that's equal to b. So that must also mean that when we square b, we get a. And then there's one other thing that's important. And, I'll put this in capital letters, and for this to work with variables, b has to be greater than equal to 0, right? By the way, are you able to take the square root of a negative number? You can, right? You get something called a complex number when you start taking square roots of negative numbers. And we will actually cover that in, I think it's, I want to say chapter 2. But for right now, we're going to deal with only real solutions of square roots. All right, so if we're dealing with variables, we're assuming if we take the square root of a variable and get something like b, if we square b, we get back to a, and then b is always going to be greater than or equal to 0. By the way, does anyone know what do we call the thing inside the radical? That has a name too. This thing is called the radicand. So you have a radical and a radicand. Okay, so with that being said about variables and square roots, if we have an a greater than or equal to 0, if x squared equals a, then that's when we say x has to equal this. Because if we want to take, so this is a little different, this a and b business, because then we're actually getting numbers. But if we're trying to take the square root of a variable, right? Like this equation, if we're trying to solve it right here for x, we're not just going to get the square root of a. It's going to be plus or minus a. We're always going to have those 2 solutions. Right? Because if we did negative 4 squared and get 16, or just 4 squared, we'll also get 16. So in order to have that in variable form, we have to make sure when we take the square root that we always include a plus or minus sign. So just also some things, because we'll see during this section. Also, if you took the square root of x and squared it, you're going to get x, right? So that would be basically just raising a square root to the power of 2. And then same thing, if you took the square root of x squared, right? Sometimes we'll say that it's the absolute value of x, depending on the situation that we'll run into. All right, so that was sort of just a, hey, here are some things you probably already have seen at some point in your life, and I'll show you how we use some of those. I'll call these definitions, or at least they're not proofs, but they're at least showing you some of the properties that we're going to use in these problems. All right, so let's look at the first type of thing that you're going to have to do for section P6. All right, so this would be finding, I'm going to abbreviate here, finding square roots of ratios. All right, we're going to find square roots of ratios. So I'm going to walk you through using some of these rules, but obviously you might immediately know what the answer is. But again, I want to have as much information in these notes as possible. So let's say you had this, the square root of 16 over 25, okay? One thing you could do if you weren't sure what you were doing is to change 16 and 25 into exponent form. So what would 16 be in exponent form? Wouldn't that be 4 squared? And then 25 in exponent form would be 5 squared. The next step would be, here's what you're allowed to do with ratios or fractions or quotients. You can split the radical to be just over the numerator and then just over the denominator. Right? So then my solution here, since I'm taking the square root of something squared, I just get the thing that's squared. So I get 4 up here and 5 down here. So that would be my final answer. So these are easy. I mean, if you had another simple one, you know, you could probably skip some steps here. So in your head, you could probably do the next 2 steps and get to the final answer right away. What would be the final answer to this? The square root of 81 over 49. Yeah, it'd be 9 over 7. So that's the way you're going to have to think with some of these numbers. The numbers will be the easiest parts of these problems. Now, if there's a number where when you take the square root, you don't get an integer, we're not going to want you to take the square root of that. Okay? There are some exceptions to that, and I'll be showing you that momentarily. All right, so that's finding square roots of ratios. That's just a quick review and how that works. So now we're going to look at products and quotients of square roots. So now we're going to be introducing some variables. Okay, so if you're working with variables and you come across something that looks like this, the square root of A times B, right? So that's a product. So it's the square root of a product. What you're allowed to do is break up that product like so, right? Just put the radical above the first variable and multiply it by the radical of the second variable. Now, some caveats again for these is that A has to be greater than or equal to 0, and B has to be greater than or equal to 0, because we do not want to deal with negative roots, negative square roots. And again, if you have the square root of A over B, go ahead and split that square root like we did in that previous example with just the ratios of integers. Now here's a warning. I'm going to put it in a box over here. We'll call it warning because some people, I've seen this mistake. If you have, now we're able to do these splitting ups with multiplication, products, and then division, quotients. You tell me, is this true? If I took the square root of A plus B Is that the same as the square root of a plus the square root of b? What do you think? Is that allowed? Not allowed. Okay? So if you have addition or subtraction underneath that radical symbol, you cannot split those up. So just beware, you can't do those. Okay? All right, so let's do some practice with this. We'll start simple. All right, the square root of 27x cubed. Now, the first thing I would have you do is split out the integers, put them in their own radical symbol, and then put the variables in their own. So my next step here would be the square root of 27 times the square root of x cubed. All right? Now I would use the rules that are just directly above this example. What could I do to the square root of 27? Can I break that up into integers where I could actually take the square root? So essentially I'm asking you to think about the factors of 27. And are any of those factors, can you just take the square root? Yeah. Okay, so I'm going to change the square root of 27 to look like this. The square root of 9 times the square root of 3. And I just using the rules I just gave you. Okay? So I broke that radical up. Now, I'm going to do the same thing with the x cubed. How could I break up that x cubed so that I can actually take the square root of something? Yeah. Perfect, right? So when you see a square root with a bunch of stuff underneath it, you have to break it up. Now, this problem is probably pretty simple. We have the square root of 9, which is 3. And I'll leave it in this form for now. You can't take the square root of 3, so you leave that alone. The square root of x squared is just x. And then the square root of x squared is x, but then you can't do anything with just that square root of x at the end. Now, you're not going to want to leave that as your final answer. You have a specific form we like. We like to have all the integers out first, so the 3 stays out here. And then any variables that do not exist in a radical, so we would move this x out to here. And then what could you do with the square root of 3 and the square root of 3x? Just to tidy this up, do you see that I could write that as the square root of 3x? That would be like the reverse process of the one I'm pointing to up here. So that's a nice, clean answer. All right. Let's try another one. Oh, here's a good one. We'll do a quotient. Okay. I'm gonna painstakingly go through steps. So I'm gonna split the numerator and the denominator first. And again, the more work you can give me, the better. All right, now that I've split the denominator and the numerator, I'm now gonna split up these products. Okay. Now let's, just because it's going to be quick, if you look at the denominator, I don't have to do anything, right? I can take the square root of 25 and get 5. I can take the square root of y to the 6th. Then what do I get when I take the square root of y to the 6th? Like if the square root of x to the 4th was x squared, it looks like you just have the exponent, right? So the square root of y to the 6th is just going to be y cubed. So I don't have to break that up at all, okay? Now the top, I do have to do something. Really, I just have to break up the integer. And I'd break that up into a square root of 4 times the square root of 3. And again, I would leave the square root of x to the 4th there because I can immediately do something with that. All right, so let's see how this plays out. So the top one, and again, you can get good at skipping steps. Like that square root of 4 is 2. That's going to go out front. And then the square root of x to the 4th, that's x squared. I'm going to put that next. And then the square root of 3 kind of just hangs out by itself. And now I do the denominator, which would be 5y cubed. Not y to the 6, y cubed. And then that's your final answer. Okay. I actually think that's probably a really good place to stop, because I won't be able to get through anything meaningful in the couple minutes that are left. All right, so if you want to put everything away, and you have your homework assignment for P5, that'll be handed in on Tuesday, we'll start the quiz. So I'm going to stop my recording.